Good afternoon. First of all, I would like to say that in the program, the name of Francesca is disappeared. I don't know why, but all this talk is inspired and also driven by Francesca. And where I would like to go, it's not working. I don't. Okay, so this is outline of my talk. First, I would like to explain something about the dynamics of microstructured solids. I need to explain some kind of very simplified Mindlin microelasticity in unidirectional case, and then in the one-dimensional approximation, And then I explained some calculations about the scattering of the pulse in the periodic multilayer, and then go to the dual internal variable theory and explain some dispersion relations and dispersion curves. Okay? So, dynamics of microstructured solids can be described by many different theories, like the second gradient elasticity, Cassira elasticity, Mindlin-Ehringen micromorphic theory, relaxed micromorphic model, or a theory with internal variables. And maybe I don't know something, but it should be somehow classified. What is maybe not better, but some. But because it is have a lot of different aspects. First, I would like to explain, not my results, about the dispersion and the band gaps. So dispersion is characteristic property of microstructured solids. If you have dispersion, your solids is microstructured. So I would like to extract the results from the paper of Madeo, Neff, Giba, Placidi, and Rossi, wave propagation relaxed micromorphic continua, modeling metamaterials with frequency band gaps. Some of authors are sitting here, it is good. So, what they conclude, excuse me, first conclusion is a second gradient theories not able to account for the presence of band gaps. So any kind of second gradients. It's your conclusion. So, not anymore. Okay. Next one is the classical continuum model is qualitatively equivalent to the full 18 parameters Mindlin-Ehringen micromorphic model and not able to forecast band gaps. Okay? The Cassira model is also not able to describe band gaps. And reduced relaxed model produced by symmetric Cauchy force stress tensor excludes a priori of the band gaps. What we have only this one. Okay. Only the relaxed micromorphic model is fully able to describe the main features of mechanical behavior of micromorphic continuum. Not only microstructured continuum. Okay. So just now I need to finish my presentation because answer is here. This one. So fully able. But there is another aspect of this behavior, dynamics of microstructured solids. The first one is direct computing, or full field computing. But you know, the micromorphic continua or microstructured continua very complex, and we need to calculate something. We need to have as simple model as possible. Therefore, I start with with Mindlin microelasticity in simplified form, because it centrosymmetrical, isotropic, and only 18 parameters needed to describe something. So what this is simply Mindlin notation, and everybody can open the original Mindlin paper. There is the same as is given here. And the psi here is micro deformation tensor. This is his gradient, and this is relative strain. Okay, but 18 coefficients is too much to understand anything, so we go further. First, I would like to prolong the Mindlin microelasticity theory. So this is the partial derivatives of the free energy with respect to strain, relative strain, and gradient of microdeformation. And then we go again, okay. So what is good? That the balance of linear momentum is very simple, and evolution equation for microdeformation is also simple, and rho prime is density of material of micro level, and d is the length scale at micro level. So in principle we need to calculate these equations, but it is too much coefficients, and we go further. Okay, we go to the unidirectional case. It is also given by the Mindlin itself. So the displacement vector and microdeformation tensor here is only function of one space variable, and we have only 3 non-zero components of strain tensor. All other components are 0. It is good one. Okay, I can't to go. And Mindlin is given the equation for longitudinal motion. Again, he changed the notation, and there is the new coefficients k, a lot of them, and we have the linear momentum equation and equation of evolution for the mean microdeformation and deviatoric part of that. So, but the coefficients k are expressed in the terms of material parameters given in the first slide of the Mindlin theory in this way, and it's also given by Mindlin itself, but it is still too much coefficients. And then we go to the one-dimensional approximation, not longitudinal one, but even more simple. In this case, the only one coefficient, only one term is has the 0 order of the small parameter, and other have some first order of the parameter with respect to small parameter epsilon. In this case, we have the part of deviatoric microdeformation and mean microdeformation, which is 1/3 and 2/3 of that. And then we go to the, okay, it is the same, no? Okay. So equation of motion is simple, and equation of for the microdeformation is 2-1, because before it was 2-1, but this one should be identical terms. And in this equation, if we have 0 microdeformation, we need to have the standard wave equation. So in this case, the K11 is lambda plus 2 mu, and it has a consequence for the some constraint for these all coefficients, and 2 equations, as I said before, should be the same. So we have the identical coefficients here, and the number of independent coefficients really greatly reduced, and at the end we have something like that. This is the coupled to differential equations, and I would like to express them in more short form with the identification of coefficients like that. So we need to solve in principle something like that. But first I would like to consider the problem. The problem is again as simple as possible. We have some loading here from the left hand side, and put two different material here. This is one, this is another one. So the layer size is 120 time steps, and in homogeneity size is this one, 960 time steps. The materials are chosen as by chance by titanium alloy and aluminum with this density and Young modulus, and this one. And what we have is linear elasticity, so we have no dissipation, energy conserved, so only dispersion, and low velocity impact without plasticity effect, without nonlinearity effect, and the same numerical procedure for all cases, and all the coefficients are the same in all cases. And what we have for the initial pulse have the 100 time steps, not time steps, space steps wavelengths, and this is simply pulse. And what we have as a result of direct numerical simulation of the scattering of the pulse. This one. This is initial pulse. This is two transmitted pulses are formed somehow, and this one is some reflections because of these results of reflections of all these layers. This is direct numerical simulation without any modeling. Okay? So, this one is pulse transmission predicted by Mindlin microelasticity. So we have initial pulse, we have final pulse. It's not good, and we try to choose some fitting coefficients in this Mindlin model, and try to change this coefficient A in our model, and the situation is even worse. But what we have, the conclusion is that if we have short wavelengths in the pulse, Mindlin theory is not working exactly. It's working only for the long wavelengths, like it is definitely claimed by Mindlin itself. Okay? But at the same time, there is possibility to predict or calculate the same problem with the same numerical method by means of the microstructure model with internal variables, which is more suitable because it predicts at least two pulses which we have in the first one, like that. Of course, there is no reflections because it's model, but not the exact solution. But it looks good. But what's different between the Mindlin microelasticity model and microstructure evolution with internal variables? These are almost the same. The difference only in these two signs, nothing more. These signs are reflected also in the free energy, which is in Mindlin microelasticity in the one-dimensional form, and in microstructure model, only these signs are different. What does it mean? changing sign here means that the free energy is not convex. It is quasi-convex only, but it is, in principle, it is more or less normal results, because you see, we have not the homogeneous material. For homogeneous material, we have the convex free energy, but we have two materials, in principle, okay? So, if this model is good for the direct numerical calculations, we also can generalize this in this way, with full quadratic free energy density, and see what about dispersion and prediction of band gaps also. So, the corresponding stresses for this model can be calculated as the partial derivatives of the free energy with respect to corresponding gradients, and so also we have calculated so-called interactive internal forces, and obtain as a result the balance of linear momentum with coupling with all these gradients, and evolution equation for internal variables which are symmetric due to the conservation of energy, and both of them are here. And what is interesting, it is duality of internal variables. The time rate of one is governed by second one, and time rate of second is governed by first one. So it's duality between these two internal variables. What I would like to say, this is the derivation from the theory of dual internal variables, but the same identical evolution equation for internal variables can be derived by variation principle, but I'm skip this just now, because you see, if we go to the dispersion relation, we consider harmonic waves with wave number k and omega as a frequency, and dispersion relations in the matrix form here. But you see, all these G1, G2, F1 and F2 are given here. It's enormously complex, but I simply show you final results about dispersion relations. First of all, we introduce characteristic frequency and characteristic wave number, and then we choose the best choice for them are the one of coefficients which were previously given, and then some notation are changes to obtain as simple dispersion relations as possible. And here we have 6 independent material parameters, because B1 and B2 can be chosen equal to 1, because it is simply non-dimensional point of the starting optical curve of dispersion relation. Okay? And now I would like to show you dispersion curves which we obtain for some numbers. If we choose C2 is 0, we have only 4 coefficients, and we start to the variation of dispersion curve dependent of values of dimensional parameter C1, and we have if we change C1 goes to the down, we obtain that the acoustical part of this dispersion curve goes down and down, and here we can see some kind of band gap, but we fix the previous value of C1, still take C2 is 0, and see what happened if we change the parameter A1. And again, if you increase parameter, we increase this size of the band gap. And band gap, you see, this is dimensionless. It's maybe as much as possible, and the doctorand student of the Professor Stegman take the optimization program for the choosing of these parameters to have the as much band gap as possible. And this
ask us how to pronounce this name. Maybe the Turkish present can teach us. Okay.
So you can see that this band gap is enormously high because it is non-dimensional. So these all coefficients are non-dimensional. So choosing some parameters of our material, we can obtain something, I don't know which one. Okay? So this is final result. And I would like to say that microstructure model with dual internal variables forecast band gaps depending on material parameters at least in the same way as the relaxed micromorphic model can do that. But at the same time, the prediction of this model for the scattering of pulse by a periodic multilayer is much more close to what we have for the direct calculations. Yeah? And the relaxed micromorphic model gives the same one-dimensional equations like Mindlin-Ehringen micromorphic model. Okay? So, and dual internal variables approach provides evolution equation, which can be derived also via variational principle. Thank you very much for your attention.
Questions, comments?
Just a bit to understand. You said that you can predict band gaps when the free energy is non-convex. Non-convex, so it's some non-positive definite.
Yes.
So then you showed the last results. But I didn't understand what are the meaning of the parameters. So you are using a non-convex energy?
Yeah, quasi-convex. Quasi-convex, in reality.
Okay. And that parameter A, what?
Oh, yeah. It is difficult to understand what does it mean, this parameter. But in principle, it is not so difficult because it is the same as in this free energy. This parameter is connected to this one, so it is some coupling coefficients between the internal variables and the gradient of in strain, simply. So it is really material parameter. In the last result, it is non-dimensional, so it's very difficult to understand. Yeah.
Okay, Luca?
I think that the key point in order to obtain a band gap in an homogeneous material is to have some degree of freedom that take all the energy at that frequency. So it is crucial in your derivation that you have a dual internal, that you have internal variables.
Yes.
But in fact, it is sufficient. It would be sufficient also only one internal variable. Let us assume an homogeneous material, and you attach to each point a mass print system.
No.
Then the position.
No. I'm absolutely no.
I can prove in.
No. 5
minutes.
No. If we have only one internal variable, we have no description of optical curve at all.
Yes.
So it is not band gap at all.
At the coffee break, 5 minutes, I will show you.
without optical curve.
In proper direction.
It is easy, so
Okay.
nothing to say.
Okay. Maybe more questions, comments? Emek,
Do you
short
think that it's
question.
possible that we have a machine which is measuring all these frequencies, and then we have this frequency gap, and then out of that, by using just a linear regression, we can find out all these A1, A1 prime, B1, B2, and so on. Is this possible? I mean, because you are showing nicely in the end, you are getting these results with band gap. If we have a material structure which is producing that, can we get these A1 and A1 prime?
I don't know, because you see, I simply show that this theory can at least produce the same results as the relaxed micromorphic theory. This is first. This theory is also can produce the results which are more or less similar to the direct numerical simulations. Next step is what you say to me. Can we really describe some material which is produce some this kind of properties? I don't know. Maybe not. Maybe, I don't know. Simply.
If I may, I can say that, okay, we have dispersion curves.
Yes.
But they're just a result of differential equations. And dispersion curve is just a root of just some equation. And equation, the shape of this form of this equation is different for different models. And so you ask in the same question, you know roots, can you restore the equation given these roots for you? In general, no. If you assume Z, okay, you can. Wolfgang?
Just for my education, because this was very mathematical and I could not follow everything. Is this used in stealth technology for a cloaking device in particular?
Of course, it can be, but
Is it? Is it?
It's very secret. We will do it immediately after the answer.
No, seriously. I mean, is this the way how they make something invisible against certain radiation?
As I know, for example, seriously, such devices like mass springs was used to decrease, not to hide completely, but to decrease the noise of submarines.
The noise of
submarines.
submarines.
Very
good.
Of course, you are right, and if we can construct something which materials which have the same, but you see, it is not exact solution. The internal variables model is some kind of homogenization. So it's not give you the direct method. There should be some kind of, I don't know, construction from the material with such kind of properties. It is not the direct guide of that, no. It is homogenization.
Thank you.